In this demonstration we're going to look at finding the areas of the shaded sections under this curve y equals x squared, and we're just using this as a simple idea. It's a simple function, y equals x squared, and I think what we'll do is, if we integrate that first, then the integral of x dx is x cubed over 3 plus c. Now, because I'm using the same function each time, that part of it will not change. However, when I look at part A, I'm looking at a particular part of the graph. I'm looking from 0 to 5. So when I'm going from 0 to 5, my question looks like this. It's the integral of 0 to 5. 5 is the upper limit, and 0 is the lower limit. And so what I'm looking at is the area between those two limits. And I'm looking at the integral of x squared dx from 0 to 5. Well, clearly that's going to be x cubed over 3 plus c. That won't change. But what I'm now doing is I'm going to say I want to evaluate that between 0 and 5, where 5 upper limit, 0 lower limit. And this is now written as 5 cubed over 3 plus c. Take away 0 cubed over 3 plus c. And so what I'm doing here is the upper limit, which is the yellow one, is placed in the first bracket, and then I'm subtracting this value here. So this will give us 125 over 3 plus c minus 0 over 3, which is 0, minus c. Notice plus c minus c disappear, and that's going to happen every time. So the area under the curve y equals x squared between 0 and 5 is 125 over 3 square units. It can be square centimeters, square meters, anything. Often we just leave it as a number without any dimensions there, any units. And comparing that to the values on the Illuminations website that we were looking at, this is 60, no it isn't, I beg your pardon, 6 into 12, it's 40, 1 and 2/3, which is that. So that's it. Part B is a strip. We're going to look at a strip between 3 and 5. Well, clearly, in order to get that strip, I need this light blue one that I've just calculated, and I'm going to subtract this bit right here. Okay, and this is where this subtraction idea comes in. So, how does it look? It looks like the integral between 3 and 5 this time of x squared dx. Clearly, the integral is going to stay the same, x cubed over 3 plus c. The only difference is the conditions of the upper limit and the lower limit. Okay, so the upper limit is 5 again. The lower limit is this time is 3. How does that change things? Well, not a great deal. This is 5 cubed over 3 plus c. Then I subtract that other piece, which is 3 cubed over 3 plus c. Again, there's the yellow 5, which is the upper, and there's the green 3, which is the lower boundary. So this gives us 125 over 3 plus c minus 27 over 3 minus c. And again, look what happens. Right, these are definite integrals now, because the c, the constant terms, have been taken care of. This one was 98 over 3 square units, which is, if we do it in decimal form, is 3, 2 and 2/3. So we're looking at that. The third one looks a bit different, but it is still an area under the curve, except that the boundaries are now, the lower is -3 or -3, and the upper is 4. So we simply go integral lower boundary is -3, upper one is 4, let me just check that, yep, of x squared dx equals x cubed over 3 plus c between -3 and 4. Putting in these values, there's the upper limit, there it is again, there's the lower limit, there it is again, and all we're going to do now is 4 cubed over 3 plus c, subtract -3 cubed over 3 plus c, again showing you where those values are substituted. Okay, 64 over 3, c, minus, well that's not -27, so plus 27 over 3 minus c, lo and behold, c's disappear because it's a definite integral, it's got a definite answer, and the answer is 91 over 3. And again, just to compare it with the Illuminations website, that will be 0.3 recurring. And that's it, done.